Welcome back. Combinational logic versus sequential logic. Up until this point, we have been dealing with combinational logic. That is pure logic, where the output is completely dependent on what the inputs are. Today, we'll be moving to sequential logic, which is logic that has memory. Which is to say, the output is no longer dependent only on the input, it's dependent on the input and the history of the past. In the lab, you did construct a sequential circuit. It looked like this. This is a motor control circuit. We have a stop button and we have a start push button. This also goes by the name of 3-wire motor control. We call it a latch. We could also call it a seal-in circuit. By the way, it's called a 3-wire circuit because these are the wires that you need to run to the switch box. There's 1 wire there, there's 2 wires, and then there is 3 wires. Uh-oh, it looks like we made a mistake. This should be a closed contact. You remember how the motor starter works. There is an overload block, and that overload block has a normally closed contact. Should the motor cause an overload, this contact will open and disable the motor. Now, we said a sequential circuit has memory. So where is the memory in this circuit? Here's how it works. When the start button is pressed and the stop button is not pressed, coil K1 will be activated, right? This rung here will evaluate as true. As soon as that happens, K1 will activate and it will provide this second path. It will be a path that powers itself. You could think of that as sealing in its own power. So again, that's where that term seal in comes from. Again, because this is an alternate path, K1 will now hold itself independent of the start button. In fact, we could entirely remove the start button and the circuit would stay activated. Okay, that's memory. The output, K1, is dependent on memory. It's depending on conditions that happened in the past. The circuit will remember that the start button has been pushed. It will stay activated until the stop button is pressed or until you remove power to the circuit. When the stop button is pressed, you can see that this line here is broken, which will deactivate K1, releasing the latch. Just remember that K1 is our memory. It remembers that the start button has been pushed, and it will latch itself on via this circuit right there. If this was a digital logic class, we would have used language like this. We would have said we have 2 states. We have an off state and we have an on state. You can transition from off to on by pushing the start button. You can transition from on to off by pushing the stop button. There are 2 more loops here. If you are in the on state and you continue to push that start button, you will stay in the on state. If you're in the off state and you continue to push the stop button, you will stay in the off state. Okay, so this is what we call a finite state machine with states off and states on. And that refers directly back here to relay K1. K1 has 2 states. It's either off or it's on, and it's held on via its own contact. This is a very simple finite state machine. We could certainly build one with much more complexity. You may recognize that as a washing machine. We will get to this point, but it's going to take a few more lectures. For now, let's just stick with our two-state sequential machine, things that are either on or off. Let's start by taking a closer look at this circuit here. If we were to generalize, we would describe an activation logic. On that same rung, we find release logic. And then, of course, the coil. And we'll call it Boolean latch. On the branch, we would find a contact from the Boolean latch. We may also find other holding logic. And of course, that is ORed with the activation logic. And it is this contact which seals in power. We could say it seals in the Boolean latch. By the way, I should mention that this circuit in here would be normally closed logic. Our activation circuit would be normally open. An example of that was the start button. And in here, this would be normally closed, for example, the stop button. I think we saw that over here. So our start button was normally open, and our stop button was normally closed. While we're here, we should put this into words. We would say the latch is memory, in that it holds the state of the system. It's initiated via the activation logic. It is held or sealed in via the holding logic. And finally, it is deactivated via the release logic. We should make a note. These two can be combined, which is to say, this release logic could be moved down here to this branch. And while that works, you have to be careful, because in some situations you can end up in an unsafe condition. For example, if you were to move the stop button down here, and if the operator pushed both the start and stop button at the same time, what would happen is the start button would override and the machine would continue to run. So you gotta watch out for that. All right, folks, we are back here again talking about the memory models of the PLC. The concept of time is something you're always going to have to keep in the back of your mind when we start talking about these memory operations. You have to remember that the PLC is always going through this hardware-based operation where it's scanning the inputs, your programs do something, and then it sends that information to the outputs. But you also have to remember that your programs are scanned sequentially, and the PLC walks rung through rung through rung. Let's see if we can't represent the PLC operation using a spiral. The PLC starts, and it goes through a scan. So there it is. There's the first program scan of the PLC. It continues on. So now we've completed 2 program scans. Now we do a third one. Okay, so we're ever spiraling out. For sake of argument, let's assume that the operator pushes the start button right here. So here we have a start button. We know that that will not be detected until the PLC does its input scan. So right here, we detect that the button has been pushed. Peekaboo, right? So we detect here. Your code will handle it here. So we're going to put a 1 here. And at that position 1, this is what we see. The ladder logic is like this. So this is our start button. This is our normally closed stop button. And we'll see that the Boolean latch is activated. Okay, so that's what happens at position number 1. We then continue on with our scan, and we end up here at time 2. Okay, so 1 scan later, this is what our code looks like. Our start button may or may not be held. Our stop button has not been pushed. But this condition here is true. Our X latch is closed. So now we have continuity through this rung, which holds the latch closed. If we add another loop on our spiral, and if we assume that the stop button has been pushed here, the stop button will be detected here, and it will be handled here. Our code looks like this. We already stated that the stop button has been pushed, it's been detected, and we've declared that we're here at point number 3. When this instruction evaluates the memory location, it will find that the stop button has been pushed, and this instruction will evaluate as true. When it evaluates as true, the latch will be released. Okay, I do hope that that spiral gave you a way of thinking about code in the PLC. And the reason we put that spiral in there is because sequential logic has memory. The output is dependent on the input plus the past. And the past is that loop we keep talking about. So what happened on a rung in the past will now affect what's happening to you in the present. Again, combinational logic was so much simpler. You didn't have to worry about the program scan. In fact, it didn't even exist because every condition you had when you went to the sum of product structure right here was what you had. You didn't have to worry about it. When you got to this point in the code, it just handled it. It didn't care about the past. All right. With that said, let's work a few examples. In this example, we'll write a rung of code that will latch when condition A and B are true. We want the latch to be released when condition N or condition M. The logic would look like this. First, we have our activation circuit. We describe this as a logic AND. So Boolean B, Boolean A, leading to the latch. We know that the latch contact must appear down here as part of the holding circuit. Let's give us a little more room to do this. So here we have the activation circuit and the holding circuit. We need to add the stop circuit or the release circuit. to do that, we can break this here and here. And if we add two normally closed contacts, one for Boolean n and one for Boolean m, we are all set. This circuit will latch when both B and A are activated, so that will evaluate as true. Assuming we aren't activating N or M, this will also evaluate as true, enabling the latch coil. That will close this contact, completing our latch. Let's try another example. We want to enter a fault state when not C or the product of not B and not A. We said not C or the product of not B and not A. We want to clear the fault when reset is pressed. And we'll let that be a global Boolean. That circuit looks like this. We have Boolean C. Actually, we have not Boolean C. We have not B and not A. Right, so that completes our activation circuitry. We have the reset, and we have a coil called fault. So this is our activation circuitry, and this is our release logic. What we're missing is the holding logic. And that goes right here as contact Boolean fault. Okay, so again, that is our holding logic. So activation, hold, and release. This is a good time to introduce you to a few new types of coils known as set and reset. They look like this. Suppose you had that start button and you ran that to a coil called Boolean latch. You notice there's an S in there for a set coil. Then suppose we have our other push button, we'll call it stop, and you ran that to the counterpart of a set coil known as the reset coil. You'll notice this is something new because both refer to the same memory location. You'll also notice that both the set and reset are active high. For example, if you wanted to set the memory location called Boolean latch, this rung would have to evaluate as true. Likewise, if you wanted to reset the memory location called Boolean latch, this rung would have to evaluate as true. It might help if we show what's going on inside this set coil using our stick figure. Not much to a set coil. You've got your hero sitting in here watching this input. We'll call it the enable line. And if the enable is true, the only thing that our hero can do is move this lever to the true position. That's it. There is no false position. The reset instruction looks remarkably similar. In this picture, all our hero can do is move the lever to the false position. You'll see that all they have is a single pole, single throw switch. Right? Single pole, single throw, that's all they've got. The only thing that the set coil can do is take that lever and move it to the true position. That's it. It can only write a 1 to memory. Whereas the reset can only move that lever to false. The only thing it can do is it can put a false into memory. Other than that, it leaves the memory alone, which is to say the set instruction can never write a false to memory. It simply can't. There's no mechanism for it to do that. Likewise, the reset can never write a true to memory. If we come back here, this might make a little more sense now. If Boolean start evaluates as true, our set coil will write a 1 to the memory location called X latch. Or if the stop button is pressed, our reset coil will write a 0 to the memory location called latch. We can demo this in connected components. We will turn on the simulator.
Power the simulator on. Then we will download the code to the simulator. Download. Download. Yes, we want to run.
In this particular example, we have 3 sensors, one for overtemperature, another for overtemperature, and then one for a low water. And all 3 of those are ORed together, so if any one activates, we will trigger this fault condition. So if we go over here and we right-click on that and we toggle that value, you'll see that this rung has evaluated as true, and our global Boolean fault is now set. And even if we release that sensor, this coil is still set. So it has memory. To clear the fault, we push the reset button, and we see that this has evaluated as true, but now this memory location, our global Boolean fault, is clear. That's kind of an interesting condition you see here. We have red indicating that it's evaluated as true, but yet we have a coil that says it's not activated. And that is indeed what has happened. This memory location is now false. Going back to our scratch pad, let's work these examples again. So in this example, we said we're going to latch when both B and A, and we're going to stop when N or M. So let's do that code using set and reset coils. The activation circuit is still the same. Boolean B, Boolean A. We're going to send that to a set coil. We're going to call that Boolean latch. Okay, so nothing really changed there. Boolean B, Boolean A, going to latch. That was our activation circuit. Our release circuit now looks like this. It's an OR condition. Going to a reset coil. And this was N and M. So if either N or M, we will reset our latch. Either N or M, we will release the latch. The other example was down here. We want to enter a fault state when not C, or the product of B naught, A naught, and we want to clear the fault when the reset button is pushed. Using set reset coils, that looks like this. So here's our not C. Here is the product of not B and not A. Going to a set coil, and we called that fault. So Boolean fault. The reset line, we had Boolean reset, and we will run that to a reset coil, again pointing to memory location Boolean fault. Bouncing back to connected components. we had this example where we have 3 sensors, 2 temperature sensors and a low water level sensor. And those are used to set a fault in our machine. And this is a reasonable circuit. It will certainly work. However, you will not know which of these 3 has activated. Say, for instance, this sensor activated. If we were to arrive at the machine at this very instant, we would say, oh, it was temperature sensor number 2. However, chances are you're not going to be there right away. And this machine, which was too hot, went into a fault state. The fault state is probably going to shut it down. And as soon as it shuts down, well, guess what? The temperature sensor goes away. So now the only thing you can tell is that it was in a fault condition, and you have no idea what caused the fault. You might find this interesting. If we were to take those sensors, so here's that same sensor 1, here's sensor 2, and here's our low water sensor. If we were to put them on their own rung, you'll notice we have this coil here for fault, this coil for fault, and this set coil for fault. So instead of having them ORed together, right, instead of having them ORed together like this, we've given each one its own set coil. We've also added this new piece of code called a move instruction. And the first thing you need to know is that when you have something that says enable, right, if we have an input labeled EN, that means enable, and we have this output labeled ENO, which is enable out, just know that internally there's a wire connected between these two. We would see this if sensor 1 were to activate. This line would evaluate as true. The enable would be passed directly to enable out, and we would latch in our fault via the set coil. At the same time, this move instruction would take the 1 that's in this location, and it would transfer it over here to the error code. The same thing would happen on rung 2. If this temperature sensor were activated, this would evaluate as true, this would evaluate as true, we would latch in the fault, and the number 2 would be transferred over to error code. Same thing for rung 3. Let's give it a try. So we activate it, and we see the number 3 has been transferred over to 3, and we see that we have entered a fault. Okay, so we have latched in a fault condition. You may have noticed these contacts over here. What they do is, as soon as a fault occurs, they prevent any subsequent faults from overwriting the error code. So if we clear this, and then we go to sensor 2 and we activate it, you'll see that the 2 does not get transferred over. It stays as a 3. Likewise, this one, if we were to toggle it, right, we don't get that error code. It stays as number 3. So this circuit here essentially locks in the first fault, and it provides that error code to show what's going on. To reset the block, we come here. By the way, there's another move. So if this line activates as true, then 0 will be transferred into our error code. Let's give that a try. So we toggle that, and sure enough, it has evaluated as true. Our error code is now 0, and we reach this condition here where the rung evaluates true, but the memory location is 0 because it has indeed been reset. While we're here, I wanted to show you another piece of code that'll just make you tear your hair out. Goes like this. We have a machine with a lighted push button. So you may have seen that. You have a panel. You have a panel and you have a single push button. That push button is labeled run, stop. If you push it once and release it, the panel light will come on, indicating the machine is running. And if you push it again, the panel light will go out, as will the machine. That start-stop push button has been mapped to this global variable location called run stop push button. That is passed through a rising edge trigger detector. And the way this works is as soon as that push button is detected, right, as we go through the program scan, as soon as it's detected, this Q will be high. and it will be high for exactly one program scan, which means you end up with a pulse. We've called that Boolean rising edge pulse. If we go to rung 2, this says if there's a rising edge pulse, which means the operator has pushed the button and this location called toggle is not activated, we are going to turn on the Boolean location called toggle. Simple enough. The third rung is similar. We see that pulse again, and this says if there's a pulse, which is to say the operator has pushed the button for the second time, and you're in toggle, which is to say the light's already on, the system's running, you will turn off the system. So let's see if it works. So we go over to our push button, and we push it, and nothing happens. So we try again. We push it, and nothing happens. Well, a couple of things here. First, on your simulator or when you're viewing connected components, you will never see a pulse, right? At no point will you ever see the output of a rising edge trigger go red, okay? So you'll never see it. However, you should have seen the toggle activate, because if there was a pulse, and we assume there is because, you know, this did go red, right? So we knew this evaluated true at least once. So if that pulse occurred, and we can clearly see that this is activated, we should have set toggle. Interestingly, we did. This code did exactly what we told it to do. So that pulse came through, the pulse was here, this line evaluated as true, and it set the toggle. Done. However, on the second rung, our pulse is still there because we haven't done anything with it, right? That pulse will be high for one program cycle. So this is still true. What's the condition of this at this particular moment in time? Well, it's set, right? Because this line right here, set, toggle. So now toggle is set, which means this line evaluates as true. So if that line evaluates as true, we clear toggle. I'll tell you right now, this is something that will drive you absolutely crazy because you'll run into problems like this and the code looks good. And when you examine any individual rung, it makes perfect sense. If there's a pulse because you push the button and your system is not on, turn it on. If there's a rising edge of pulse and your system's on, turn it off. It makes perfect sense. But when you put the two together and you see how the system is operating, you see that rung number 3 undoes rung number 2. We can solve this problem by making one minor correction to the code. So we have the same code. Here's that run stop push button. Here's the rising edge trigger. Here's the pulse. Nothing changed there. If the pulse occurs and you're not toggled, turn toggle on. Let's push our run stop push button and see if it functions. And we see it does. So when this evaluates true, we get a pulse, right? That pulse will come here to rising edge pulse. On rung 2, that pulse will be here. This will evaluate as true, and that will activate our toggle. Right now we see this in blue because you can never see a pulse in connected components. However, we know that it did occur because this line here evaluated as true at some point to activate toggle. I'd like to direct your attention to this little rung right here. What this says is whenever you set toggle, right, the first time the operator pushes the button, you're also immediately going to clear, right, with a reset coil, you're immediately going to clear this memory location called rising edge pulse, which means that this here will never be set, and this line will not evaluate as true. So instead of rung 3 undoing rung 2, it actually does what you intended it to do. We can see that if we come over here and if we toggle that push button. All right, so here we are. We can turn it off very quickly. So Push button once, push button off, push button on. There we see it activated. Push button off, and this is the second press, and it clears toggle. Okay, so that is one way to handle that. Before we leave, I wanted to point out a few things. You'll notice that this here is a direct coil. It is associated with the memory location rising edge pulse. Down here is a reset coil. It is also associated with the Boolean rising edge pulse. You'll notice there is no set coil associated with this. So set coils and reset coils don't have to come in pairs. You could have one or the other depending on what you want it to do. If we were to put that into words, we would say we can mix and match coils. And in connected components, we have 4 different coils. We have the direct coil, which can write a true or a false. We have the reverse coil, and you may be tempted to put an R there, but don't. That would be wrong. The reverse coil has a slash like that. The reverse coil can also write a true or false. We have the set coil, which can write only a true. And finally, we have the reset coil, which can write only a false. Okay, we've covered a lot of material today. Next time, we're going to explore data types. A few lectures from that, we're going to explore built-in functions, and then control structures. And all of that will lead to something called the user-defined function block. And once we're there, we can move to sequential machines. And what are sequential machines? They go like this. If start after 2 minutes, if greater than 2 minutes. Well, I think you get the point. What we're trying to say is that the user-defined function block will open up many memory locations and allow us to program these complex behaviors.